So having learned how to calculate the total angular momentum of an atom or an ion, we're now going to look at how to translate that into the magnetic moment of the object. Okay, so for an atom with total angular momentum J, the magnetic moment is given by this hopefully fairly familiar formula here. So we need to take the square root of J plus 1, and that will give us mu b lots of magnetic moment with the appropriate G factor out the front. Okay, so this is very similar to the formulas that we had for orbital angular momentum or for spin angular momentum, just with the appropriate quantum number here and the appropriate G factor. Now, the appropriate G factor for our multi-electron atom is the Landé G factor, and it's defined by this longish formula here. Okay. We're going to look at some examples of using this in a moment. What I will say is that you do not need to memorize this formula. There's no point memorizing it. If you need to use it in an exam, I will give it to you in the question. Okay. So we've got potentially a procedure here whereby we've got a multi-electron atom. We can use Hund's rules. We can work out big J, S, and L. We can then work out the magnetic moment by working out the Landé G factor and popping everything into this equation here. We can then compare the magnetic moment with experiment, for example. Okay. But it's instructive perhaps to look at a couple of limiting cases. So first of all, let's look at the case in which there is no net spin, so all the electrons are paired. So let's imagine we've got S is 0. In this case, J will just be equal to L. And if J is equal to L, then, so this term is 0, and these two terms will cancel out. So the fraction here will give me 0, and this means that G is just equal to 2. Sorry, G is equal to 1. Okay, that's exactly what we found for the case of orbital angular momentum in a single electron. Okay, we didn't actually put a G factor in them because it was just 1 and it wasn't, so there was no need to put that in there. But this is a more general case that if I've got a multi-electron atom where there is no total spin angular momentum, okay, the angular momentum is purely from the orbital part, the G factor is 1. And in the other limiting case, so if L is equal to 0, then J is equal to S. Okay, J is equal to S, this term goes away, these two terms add up, but they're equal to the thing on the bottom, so the fraction just gives me 1, and then I do have G is equal to 2. And so this is exactly what we found in the case of a single electron spin. So this is now true more generally. So if we've got something like a half-filled shell and L is 0 and we've only got spin angular momentum, then the appropriate G factor is just 2. So let's go on and look at some examples. Okay, let's look at the case of cerium. So cerium 3+. We know that's got a xenon core, and it was 4F1. And we found earlier that L was equal to 3, S was equal to 1/2, and J was equal to 5/2. Okay, so the Landé G factor, we need to use the formula 1 plus J plus 1 plus S plus 1 plus, minus L plus 1 all over 2J plus 1. Okay, right, sub things in. Okay, sub in for J, so 5/2 dotted with 7/2 plus 1/2 dotted with 3/2 minus 3 dotted with 4, all divided by 2, that's 5/2 dot 7/2. Okay, and that's going to give me 1 minus 1/7. So this will be equal to 6/7. So the G factor now is neither 1 nor 2, it's 6/7. Okay, so in general, we're going to end up with a non-integer G factor. So if I go now to evaluate the magnetic moment, mod M is equal to G square root of J plus 1, lots of mu B. So this will be 6/7, the square root of 5/2 dotted with 7/2, lots of mu B. So this is 2.54 lots of mu B. And if we compare with experiment is 2.4 mu B. So that's quite interesting because we've avoided doing some horrendous calculation on a multi-electron atom. We've simply taken our Schrodinger picture and Hund's rules, empirical rules for how to add together angular momentum, and we've managed to predict the magnetic moment of the of this cerium 3+ ion to reasonably good agreement with experiment. So this is going to enable us to understand some of the trends that we can see in experiment. Okay. Let's look at a few other examples. And what we can do is that I can write the first bits down, and if you'd like, you could just pause the video and see if you can work out the G factor and the magnetic moment. Okay. So I'll just write the first one in for checking. Okay, so we've all got them on the same page. Cerium 3+. This was L is 3, S is a half. J is equal to 5/2. Okay, so if you want to pause and then just see if you can calculate both G and the magnitude of M. So we found that G was equal to 6/7. M is equal to 2.54 mu B. And the experimental value was 2.4 mu B. All right, so that's the first of our F elements. Let's do the second F element. So that was holmium 3+, and we found that was L is 6, S is 2, J equals 8. So if you want to pause and calculate what G is and what the magnetic moment is. So G is going to be equal to 5/4, and the magnetic moment is quite large. It's 10.6 lots of mu B, and experimentally it's 10.4 mu B, so another good prediction. Okay, let's look at so they were the 4F elements. We did two 3D elements. Okay, we did first vanadium 3+, and we found that to be L is 3, S is 1, J is equal to 2. Okay, so if I do you want to pause for a moment and then have a go at calculating it. So if you do that, you get G is equal to 2/3, and M is 1.63 mu B. And experimentally, we get 2.8 mu B. That's not great. Okay, that's not the sort of agreement we saw before. Something isn't quite right. So let's go on. Let's look at the next one. Let's look at manganese. Okay, so manganese 3+. Here we found that L was equal to 2, S is equal to 2, and J is equal to 0. Now, I invite you to pause and just think for a moment. You're going to have a problem with the formula for G. But really, do we need G? What we need is M. So maybe think about if you can calculate what M should be, and maybe we don't need G. Okay, so indeed what we found is that G is not particularly meaningful, but remember what the magnetic moment is defined as. It was G lots of square root of J plus 1. And, if J is 0, then there's no magnetic moment. We don't have to worry too much about what G is. Okay, the formula that we used isn't really valid for J is equal to 0. But on the other hand, the magnetic moment doesn't exist. So according to the prediction, so we don't actually need to really understand what G is at that point. Okay, so we ignore G. And M is 0 because there's no magnetic moment. How does that fit with experiment? Well, it's a bit rubbish. 4.9 μb, miles off. So this is quite interesting because we found that when we looked at the 4F elements, our theory was really very accurate. But when we came to look at the 3D elements, it really wasn't predictive at all. Okay, so what's going on? Yep, here's a summary of that, although I think that one shouldn't be there. Okay. So let's try and understand this. What we find is that for 3D elements, the orbital angular momentum doesn't contribute to the observed magnetic moment. The 3D and the 4F are both quite localized orbitals, but the 4F is really very localized, and the 3D is not quite as localized. And what that means is the 3F orbital interacts with the crystalline lattice. Okay, so we've got a crystal, and this orbital is locked into the crystal orientation by by the electrostatic electric field that exists in the material. So when you apply a magnetic field, let me try and draw a sort of vague schematic sort of diagram. So we've got our crystal, okay, and here we've got our orbital sat somewhere in the crystal, okay, and what we want to be able to do is apply a B field in lots of different directions, okay. So our B field might move in lots of different directions. And what we'd expect is the magnetic moment should be able to follow that. It should be able to change and turn as we apply the B field. But in the case of the 3D, this orbital is locked in place with by the electric field in the crystal. So it doesn't respond. The only thing that responds is the spin angular momentum. Okay, so the spin angular momentum can respond. So what we say, what is common in the field, is for people that say the orbital angular momentum is quenched. Okay, it doesn't contribute to the magnetic moment. Whereas in the case of the 4F, the 4F is much more localized, and that means that both the spin and the orbital part can respond to the magnetic field and can move as the magnetic field direction is changed. Okay. So if that hypothesis is true, we should be able to calculate the magnetic moment of the 3D elements, but only bringing into account the spin. Okay. So let's go back, and if I wanted to look at my vanadium 3+, I'm just going to take into account the S is equal to 1 state. Okay, and we know now the G factor is 2 because this is pure pure spin, and so the magnetic moment was going to be the G factor square root of S plus 1 lots of mu B. Okay, so remember here that L is 0 and J is just equal to just equal to S. So if we do that, we're going to get that mod M is equal to 2 times the square root of 1 times 2, lots of mu b, which is 2.8 mu b, and experimentally, 2.8 mu b. What about manganese? Okay, so here I've got manganese 3+. This was a very long way out before. S is equal to 2 in this case. So mod M is going to be G, which is 2, times the square root of 2 dotted with 3, lots of mu b, and that's equal to 4.90 mu b. An experiment, 4.9 mu b. So when you need to take into account the magnetic moment of the 3D states, the orbital angular momentum is quenched. It doesn't contribute, so we can set it to 0, and we just calculate the magnetic moment based on the spin, and that does a remarkably good job. The 4F, we need to take both orbital and spin into account. Now, perhaps an obvious question then is, well, what about 4D? What about some of the other potential things? They can be more ambiguous, and that can be a little bit more involved. The 3D and the 4F are quite clear cut. That counts for quite a lot of important and interesting materials, and we'll focus on those. But remember, we can recognize that perhaps sometimes some of the other elements might be a little bit trickier to work out.